I welcome you all to week 11 of this online course on digital electronics and system design. In week 11, we shall discuss about digital to analog converter, that is DAC, and analog to digital converter, that is ADC. We shall discuss about performance characteristic of DAC and ADC. We shall also discuss about different types of DAC and ADC along with their advantages and disadvantages. So, before we start, let us have idea about learning outcomes of week 11. At the end of this week, learner will be able to explain principle of DAC and ADC, describe operation of different types of DAC and ADC, analyze advantages and disadvantages of different types of DAC and ADC, evaluate accuracy and resolution of different types of DAC and ADC. So, before commencing very first lecture of week 11, let us recollect some points about analog and digital signal which has already been discussed in previous weeks. As we know, analog signal is continuous in nature and it contains infinite range of values over a finite time period. It gives more exact values, but it is more difficult to work with analog signal due to unwanted noise during recording, and if we transmit data at long distance, then unwanted disturbance occurs. At the same time, digital signal is discrete in nature and contains finite range of values over a finite time period. It is not as exact as analog signal, but it is easier to work with digital signal due to its noise resistance, robustness in transmission and many more advantages. So, the first thought that comes in mind, why do we need ADC and DAC? Most of the signals in our surrounding are continuous, means analog in nature. For example, temperature, pressure, humidity, light intensity, sound, etc. And we have many applications or systems which directly interact with this environment signal like smartwatch, health tracking system, mobile phones, etc. These systems are digital in nature because handling digital signal is more advantageous due to many reasons. Some reasons are: all microcontrollers store information using digital logic. Digital data storage is more robust and efficient. Digital data transmission is more efficient. Digital data is easily reproducible. So, in order to transmit or process analog signal as per our requirement, it is converted to digital signal using ADC. Then digital system processes it, and that processed digital signal is converted back to analog signal using DAC for precise control applications. Now, look at this schematic diagram which shows interfacing of analog world with digital system. From the environment, some physical variable like temperature, sound, etc. is taken as input. The transducer, which can be a sensor, convert this physical variable into a voltage. This analog voltage is converted into digital data using ADC because digital system understand only zeros and ones. Digital data output of DAC is processed in our digital system and some digital output is obtained. This digital output is converted to an equivalent analog voltage using DAC. Now, the analog output from DAC is fed to actuator which uses the voltage to control physical variable of environment. So, in this lecture we shall be discussing about digital to analog converter, means DAC. Let us move forward. Now, let us understand what is DAC. DAC is an electronic circuit which takes digital data as input and generates proportional analog voltage or current as output. Digital data remains in the form of binary input, either 0 or 1, which is transformed into analog voltage or current. The block diagram shows an n bit DAC because it is taking n bit digital data from D0 to Dn-1 as input and generating analog voltage A as output. A reference voltage V max is applied to DAC, which determines what will be maximum output voltage of DAC. Let us take an example of 3-bit DAC to which we are applying reference voltage of 7 volt. Table on right side shows possible 3-bit digital data combination as input and corresponding analog voltage outputs. There is total 7 possible combination of 3-bit digital inputs. Graph on left side shows input output characteristic of 3-bit DAC. Here smallest change in digital input, that is change from 000 to 001 or from 001 to 010 is known as least significant bit, that is LSB, and smallest change in analog output, that is from 0 volt to 1 volt or from 1 volt to 2 volt is known as step size. The characteristic looks like a staircase structure. So, with change in input voltage, output voltage jumps in steps, which cannot be continuous in nature. Now, we shall discuss about resolution of DAC. Resolution is a very important performance characteristic of DAC. Resolution is defined as smallest change that can occur in analog output due to change in digital input. It is also called space size and is equal to weight of LSB, that is least significant bit. In last example, we have taken reference voltage equal to 7 volt, means output changes from 0 volt to maximum 7 volt, and we have 3-bit DAC, means there is total 7 possible steps. So, here each step corresponds to 1 volt. Say if we have 4-bit input, there will be 15 possible steps and each step correspond to 7 by 15 volt. It means a 4-bit DAC has higher accuracy compared to a 3-bit DAC. So, let us have a generalized expression of resolution for n-bit digital input DAC. Number of analog levels is equal to 2 to the power n. So, in 3-bit DAC it is equal to 2 to the power 3, which is equal to 8. Number of steps is equal to 2 to the power n minus 1. For a 3-bit DAC it is equivalent to 8 minus 1, that is 7. Step size or LSB is equal to V max by 2 to the power n minus 1. So, for our last example it is equal to 7 by 2 to the power 3 minus 1, which is equal to 1. Percentage resolution is equal to step size divided by V maximum into 100, or it can be further simplified as 1 by total number of steps into 100, or percentage resolution can be written as 1 by 2 to the power n minus 1 into 100. So, for a 3-bit DAC, percentage resolution is equal to 1 by 7, which comes 14.2857%. As number of bits increases, resolution value decreases. Now, let us see different types of DAC on the basis of their design. There are two different types of DAC. First one is weighted resistor type DAC and second one is resistive ladder type DAC. After understanding the design, we shall come across a conclusion that the first type is easier to analyze, while the second type is more practical from the point of view of implementation. Let us see how these two are implemented. Let us see the first one, which is weighted resistor type DAC. So, let us have talk about n-bit DAC of this type. Circuit design of this type of n-bit DAC consists of an inverting op-amp and n different resistances values of magnitude R, 2R, 4R up to 2 to the power n minus 1 into R. Say if n is equal to 3, we need 3 resistances of values R, 2R and 4R. The weighted resistance help in generating current inversely proportional to their magnitude. The total current is added up by an op-amp and is converted to output voltage A, which we will understand through a circuit diagram. But the main drawback with this type of DAC is that as n increases, number of different value resistances increases. Now, problem is we require so many resistances of different values, which is very difficult to manufacture. So, before we understand circuit design of weighted resistor type DAC, let us understand working of op-amp as inverting amplifier. Op-amp, which is abbreviation for operational amplifier, has 2 inputs and 1 output. To work it as inverting amplifier, positive terminal is grounded and digital input D is applied to negative terminal through different resistances. Since positive terminal is grounded by concept of virtual ground, potential of point O should also be 0 volt. Now, applying KCL at point O, current incoming to point O, that is D minus 0 by R, should be equal to current outgoing from point O, that is 0 minus A by RF. Solving this equation, we get A is equal to minus D into RF by R. This equation we will use in weighted resistor type DAC circuit design. Now, let us understand circuit of weighted resistor type DAC. Here also op-amp is used in inverting amplifier configuration. Here, instead of one input, n bit digital data is given through n different value resistances. In circuit, it shows we have 4 bit digital input. Digital data is either 1 or 0. So, let us consider 0 volt indicates 0 and 5 volt indicates 1. Now, applying KCL at point O, total incoming current in circuit is I1 plus I2 plus I3 plus I4, which should be equal to outgoing current from point O, that is I. So, we come across the equation given below. Solving this equation, we get the equation shown here, which is the required analog output of our DAC. Rearranging this equation, we get this last equation, which is same as decimal equivalent of binary input, and RF by 8 into R is acting as proportionality constant. It means output voltage A is proportional to binary data input. In this way, by selecting proper value of R and RF, exact output voltage can be obtained from a DAC. So, you can understand the working of a DAC with the help of this example, in which we have taken 4 bit input 0101, value of R is chosen 1 kilo ohm, RF is 1 kilo ohm. So, by putting all the values in the equation, we get A is equal to 5 V by 8. Now, let us move to second type of DAC, which is more practical for implementation, that is resistive ladder type DAC. In this DAC, problem of weighted resistor type DAC gets solved, because it requires only two different value of precision resistors, R and 2R. For n bit DAC, n plus 1 resistor of value 2R and n minus 1 resistors of value R is required. Manufacturing same value of resistor in bulk is easier compared to manufacturing different value of resistor. That is why resistive ladder type DAC is more widely used. Circuit consists of resistance and a voltage follower circuit using op-amp. In voltage follower mode, op-amp output is connected back to inverting input terminal and digital input is given to non-inverting terminal through a resistive ladder circuit. Since feedback path has 0 resistance, voltage A at output terminal is same as voltage at terminal O. Let us calculate the voltage at the op-amp input when exactly one of the DI input is at 1, say plus V volt. Let us have case 1, where digital input is 1 0 0 0, that is MSB is 1 and other bits are 0. Look at the leftmost part of the circuit. Resistor 2R and 2R are connected between point C and ground. It means both are in parallel. Solving them, we get an equivalent resistance R between point C and ground. Now, this resistance R and resistance between point C and B of value R are connected in series. Solving these two resistances, we get an equivalent resistance of 2R between point B and ground. In the same way, solving the circuit, we get a resistance of value 2R between node O and ground, as shown in the circuit on right hand side. In this circuit, applying voltage division rule at node O gives voltage equal to V by 2. So, when only MSB is high, output will be V by 2. Now, let us see case 2, when digital input is 0 1 0 0, that is second MSB is high and other bits are low. Look at the leftmost part of the circuit and solve it in the same way as earlier until you reach point A, as shown in the top right corner circuit. Now, the circuit cannot be solved using same method, since voltage V is connected at one terminal. So, apply Thevenin theorem at point A and reduce circuit to an equivalent circuit shown at bottom left corner. Now, further reduce the circuit to get final circuit, and in this circuit applying voltage division rule at node O gives voltage equal to V by 4. So, when only second MSB is high, output will be V by 4. Moving further, let us see case 3, where digital input is 0 0 1 0, that is third MSB is 1 and other bits are 0. Look at the leftmost part of circuit and solve it in the same way as earlier until you reach point B, as shown in the top right corner circuit. Now, the circuit cannot be solved using the same method, since voltage V is connected at one terminal. So, apply Thevenin theorem at point B and reduce the circuit to an equivalent circuit shown at bottom left corner. Again, apply Thevenin theorem at point A to further reduce the circuit to get final circuit, and in this circuit apply voltage division rule at node O, voltage obtained is equal to V by 8. So, when only third MSB is high, output will be V by 8. Now, let us see the last case, case 4, where digital input is 0 0 0 1, that is least significant bit is high and other bits are 0. Again solve using Thevenin theorem from beginning and get final equivalent circuit. After solving that, you will get output V by 16 at node O. For all inputs applied simultaneously, principle of superposition can be applied to the circuit, because the circuit is a linear circuit and the final value calculated is given by the equation shown below. So, we get the final value as 8 D3 plus 4 D2 plus 2 D1 plus D naught into V by 16. So, A is proportional to decimal equivalent of applied digital input. In this type of DAC, main drawback is lower conversion speed compared to binary weighted resistor type DAC. Now, coming to the application of DAC, we can find a DAC in CD players, telephone, digital oscilloscope, signal generator, motor control, and there are many such applications around us. Let us have some review questions. Percentage resolution of an n bit DAC. So, recall the formula, we got an equation percentage resolution is equal to 1 by 2 to the power n minus 1 into 100. So, correct answer is C. Next question is, in a 4 bit DAC with reference input 30 volt, step size is. So, in order to calculate step size, we learned a formula, step size is equal to V reference divided by 2 to the power n minus 1. In this question, n is equal to 4. So, calculating the value, V reference is 30 volt divided by 2 to the power 4 minus 1, which is equal to 15, we get the output 2 volt. So, our correct answer is A. For 6 bit DAC, blank register of value 2 R and blank registers of value R is required. So, we have learned earlier that in resistive ladder type DAC, for n bit DAC, we need n plus 1 resistor of value 2 R and n minus 1 resistors of value R is required. In this question, n is equal to 6. So, we need resistor of value 2 R. So, we need 7 resistor of value 2 R and 5 resistor of value R. The next question is, mark the incorrect statement. So, here we have to find the incorrect statement. First statement given is, conversion speed of resistive ladder DAC is less than weighted resistor type DAC, which is true. Second is, weighted resistor DAC is easier to implement than resistive ladder DAC, which is false. So, the second statement is incorrect. Let us see C and D option also. Option C says resistive ladder type DAC uses precision resistor of value R and 2R, which is correct, and D option says resolution indicates smallest change in output for change in input, which is also a correct statement. So, here are some practice questions which you should practice after completing this lecture 1 of week 11. So, here is some short answer type question and some long answer type question. Try it out yourself. So, in short answer type question, first question is, list different types of DAC. So, as we have discussed the two classification, you can mention those names in this question. Second question is, define resolution. So, as we have discussed that resolution is smallest change in analog output due to change in input, and you can write the formula of resolution also along with its definition in this question. In long answer type question, the first question is compare weighted resistor type DAC and resistive ladder type DAC. So, in order to compare, you can use the circuit diagram of both the DACs, their advantages and disadvantages. Like in weighted resistor type DAC, we have a disadvantage that we have to use many precision resistance of different values, and this advantage is overcome in resistive ladder type DAC by using only 2 resistors of different values. Also, there is one advantage of weighted resistor type DAC, that conversion speed is higher in weighted resistor type DAC compared to resistive ladder type DAC. So, in this question you can explain the circuit of both the types and also compare their advantages and disadvantages. The next question is design resistive ladder type DAC. So, in this question you can make circuit diagram, derive all the equation, mention its advantage, its disadvantage, and that is it. And the last one is third question of long answer type question, explain working of weighted resistor type DAC. So, the same way you have done in second question, make the circuit diagram of weighted resistor type DAC, derive the equation for final output, write about its advantage, disadvantage and how the circuit works, explain some points regarding that. In this way you can answer third question. So, in this lecture we discussed about different types of DAC, their advantages and disadvantages, and resolution and accuracy of different type of DACs. In the coming lecture we shall discuss about reverse kind of conversion named analog to digital conversion. We will also see the advantages, disadvantages and characteristics of that type of and characteristic of different type of analog to digital converters. With this, let us wind up this lecture. Happy learning.